Okay. Can we get confirmation that I'm unmuted?
I don't know because I just have an email from Alicia that Alicia got an email from somebody.
Okay, so we will know hopefully pretty soon if I'm still muted, hopefully not. Okay, so let's start by thinking about these kinds of ring exchange processes. Okay, so as we just said, these kinds of exchange processes, they will couple the electronic spin degrees of freedom. Okay, and that kind of dynamics can be expressed in terms of an effective spin Hamiltonian of the sort I've written here. Okay, so this effective Hamiltonian will be a sum over permutations of electrons. Here, P sigma is a permutation operator acting on the spin degrees of freedom. J sub P is an associated exchange coupling, and this sign factor is the signature of the permutation. And here I've expanded out the first few terms just to give you a flavor of what this looks like. A 2-particle exchange, 3-particle, 4-particle, and so on. And each of these permutation operators can be decomposed in terms of spin operators, so you have some kind of generalized Heisenberg-like Hamiltonian. Importantly, what I want you to note here is the sign structure. Okay, there's a definite sign structure. The 2-particle and 4-particle exchange come with a positive sign. The 3-particle exchange comes with a negative sign. And this is, in fact, a rule that goes back to Esterlis, who was studying solid helium. He recognized that exchanges involving even numbers of electrons always are antiferromagnetic in nature. That is, they come with positive signs, whereas permutations involving odd numbers of electrons are ferromagnetic. Okay?
I thought it's called stain, no?
I thought it was Esterlis. Yeah. But yeah, I'll look to make sure I'm giving credit we're in the right place. Good. So how should we think about these exchange couplings? Well, remember that these exchange couplings are describing tunneling processes in which we are tunneling between electronic configurations related by some permutation. Okay, so here I've shown this to you schematically. So X is a multi-dimensional coordinate in the configuration space of the n electrons. So if I have n electrons in 2D, this is a 2n dimensional coordinate. And what I'm showing you here are two degenerate potential minima corresponding to electronic configurations related by permutation. So if X naught is some reference configuration of the electrons on the triangular lattice, then Px naught is some permutation of some subset of those electrons. And so these exchange processes are nothing but tunneling processes between these degenerate minima. Okay, yes, please.
Is this a model in which the electrons are spinless, so like there's no way to put 2 electrons on the same site?
Yes, that's right. Yeah, there's a hard core constraint. That is assumed. Yeah, correct. Very good. Yes. And then these J's are nothing but the tunnel splittings associated with tunneling between these wells. Okay, so having recognized that what we're dealing with is a standard kind of tunneling through a barrier problem, that immediately suggests a calculational approach, which is just semi-classics or WKB theory. So at large RS, which remember is a semi-classical limit when h bar is in a sense small, these exchange splittings can be estimated from essentially standard WKB or instanton methods. Okay, so in that kind of approximation, this exchange coupling or tunnel splitting has this standard WKB form. There's a prefactor h bar omega, where omega is some characteristic frequency associated with vibrations in this well. But the more important dependence is in this exponential e to the minus action over h bar, where this action s sub p is the imaginary time classical action associated with the process that affects this permutation. Okay, and you should note that this is, schematically at least has a standard tunneling through a barrier form, right? So this exponential prefactor goes like the square root of the mass times the barrier height times essentially the length of the tunneling path. Okay, so very good. And I should say that the validity of this kind of semi-classical approach has been verified by more accurate path integral Monte Carlo calculations by Dave Sepperly and company. Okay, so this is how we're going to try to estimate these quantum mechanical tunneling processes, is by appealing to simple WKB theory. Good. So what does this look like? So let's look at these ring exchange or multi-particle exchange processes in our triangular lattice electron solid. So here I've sketched for you the first few most compact exchange processes that you can consider. And here I'm reminding you of the formula from the last slide, where I've now made the actions dimensionless and packaged all the parametric dependence into this square root of RS prefactor. Okay, so indeed you see that when RS is big, these exchange couplings become exponentially small. Yes, please.
Sorry, are you going to explain like how you figure out what the potential is? I understand the schematic thing, but
yeah, so the potential is just the Coulomb potential of this system of n electrons. Yeah. So the Hamiltonian was the one that I started with.
And then when you do the two particle thing, so that they're going along what the lowest, essentially semi-classically, the
Exactly.
path where they have to both move from one position to the other, and they're
Exactly.
going along the lowest energy.
Exactly, and in doing so, what's crucial actually is it's not just, so let's look at this process. So these electrons are indeed exchanging their positions, but this is a highly correlated system. So when these guys exchange, everybody else will do a little dance to get out of each other's way and lower the action. And that's important.
And you're accounting for all of that.
Indeed. So, right. So the way we compute these actions, and I was just about to get to that. So these dimensionless numbers that are reported here, the actions associated with these different processes are computed by literally just finding the least action path, minimizing the action directly in imaginary time, to find what all the electrons need to do to minimize the action. That's it. Yes, please.
Yeah, intuitive understanding as to why these effective actions should be pretty much all the same, but it's
Yes.
optical involves many.
Yeah. So you guys are preempting me throughout, so very good question. So that's the first thing that I wanted you to know, in fact, is that all these actions are of comparable magnitude to one another. Okay, and that's testament to the strongly correlated kind of nature of this system. So the three particle exchange, you can sort of understand that they can do this process. It's sort of almost a free kind of process, whereas here, these electrons want to get out of each other's way, and these neighbors will also want to move out of the way. But the fact that these are all of so close in magnitude, that I don't have a good kind of rigorous explanation for, but it is a feature of this very strongly correlated system.
Doesn't this mean that you cannot stop at 6?
Yeah, exactly. Yes. So let me yes. Good.
So all the J's are common.
Yes, but
Jason will come.
RS. Exactly. So good. You guys should just give the talk for me. I think so. Very good. So good. All the actions, I mean, they are growing eventually. If you look at very large action, there is a trend where there's some kind of initial wiggles, but the overall trend is increasing with the number of exchanging particles. Nevertheless, there is a smallest action, which turns out to be the 3-particle action. And so that does mean something important. It means that when RS tends to infinity, this exchange with 3 particles will be the one that dominates. And according to the Thales rule we discussed, that means the ground state will be ferromagnetic. Okay, so we can make an asymptotically exact statement about the magnetism of the crystal as RS tends to infinity. That's wonderful. However,
Because of this small difference, 164 and 170.
because of this, so when RS goes to infinity, that small difference gets blown up.
I understand,
Yeah.
but still, it's small.
Well,
It's
good.
still might.
So that's my next.
It is still might.
That's my next point. Good. So this effect is important, as we discussed. It lifts a massive spin degeneracy that would otherwise be present in the system. Unfortunately, it's likely irrelevant. Okay. The reason it's likely irrelevant, well, there are 2 reasons. The first one is that if you estimate this energy scale, even under the most optimistic estimates, it's not very large. So in the kind of relevant systems and 2D materials, it's maybe tens of millikelvin, which is not prohibitive, but quite low. But the main reason actually is that these actions are all comparable, which means that when RS is finite, you're dealing with a highly frustrated magnetic Hamiltonian, and that further depresses the energy scale. So this is well and good, but unfortunately not immediately relevant. There is a way to lift some of this degeneracy that is relevant for 2D materials. So let me just briefly comment on that. And that's using a Moiré potential. Okay, so if I take my Hamiltonian, I take a 2-dimensional electron gas and add to it just a commensurate potential. Okay, this of course doesn't describe all Moiré materials, but for instance, in the hetero-bilayer transition metal dichalcogenides, this kind of simple modeling is probably not unreasonable. So here, this is an external periodic potential, the Moiré potential that is commensurate with the electron density. And here you can ask, how does this affect these exchange processes? So let me show you. So one can imagine different types of Moiré potentials. So this is a triangular lattice Moiré potential, where the electrons, which are the black dots, reside on the Moiré potential minima. Okay, and what I'm showing you, for instance, in this panel is how the 2-particle exchange is modified by the Moiré potential. So the pink curves are the exchange processes, what you get from this numerical minimization of the action in the absence of Moiré, and the thick black curve is what the Moiré potential does. So you see that the Moiré potential basically squeezes the exchange path away from the maxima of the Moiré potential. That's what the crosses are. and it just in general inhibits the motion of the electrons away from the Moire potential minima. This is the three-particle exchange. You see something similar happens, that the exchange path gets kind of squeezed away from the maxima. You can imagine other types of Moire potentials.
These little loops.
Yeah.
The red loops, they are the correlated dance you were describing before.
Yes, and those go away. Well, I mean, they become, not visible on this scale when you have a Moire potential. And that's important. We'll see how it manifests itself in a second. You can imagine different types of Moire potentials, just as in another example. You can imagine a honeycomb Moire potential. Okay, so this is, for example, a two-particle exchange now in a honeycomb superlattice. And you see again that this pink curve, which is the curve in the absence of Moire, gets dramatically modified as the path gets kind of squeezed away from the maxima of the potential. What's interesting here is actually that although the two-particle exchange is dramatically modified, the three-particle exchange is not. Okay, and the reason is that in this three-particle exchange, the electrons can kind of efficiently move along the minima of the Moire potential. Okay, if I have a honeycomb lattice, there are two kind of inequivalent triangles within a unit cell. So although this exchange process is not much affected, if I look at the other triangle in the unit cell, this one is affected. But the point is just that different geometries of the Moire potential will influence the nature of these exchange processes.
May I ask a question?
Yes, please.
So when your H2 deck, that's the bare Coulomb interaction.
This is just homogeneous two-dimensional electron crystals.
For you're talking about background.
Yes,
Okay.
exactly. Yeah. So this is a very minimal description of what's going on in some of these twisted Moire systems. Very good. So we can also look now how these cartoons manifest in terms of the actions. Okay, so this is a plot for the evolution of the actions as a function of the strength of the Moire potential in the case of a triangular Moire. Okay, so here I'm plotting the action as a function of the dimensionless ratio of the strength of the Moire to the Coulomb energy. Okay, and so what you see, first of all, is that all the actions grow. Okay, the barriers to tunneling increase because the electrons don't want to move away from the Moire potential minima. And another thing you observe is that when the Moire potential is quite weak, so here I've blown this axis up by a factor of 100, that the two and three particle exchange actions, they cross. Okay, so when the Moire potential is less than 1% of the Coulomb energy, it's in fact the two particle exchange that becomes most important. That has a qualitative implication, which is that it will switch the ground state from being ferromagnetic to antiferromagnetic. Okay, the honeycomb case is broadly similar in that the actions all grow with increasing strength of the Moire potential, but interestingly, because of this nearly free kind of three-particle exchange in the honeycomb potential, the three-particle action does not become larger than the 2-1 until much, much larger values of the Moire potential. So the Moire potential has to be 2 orders of magnitude deeper to stabilize an antiferromagnetic state over a ferromagnetic one. Okay, so the point is that in a triangular lattice Moire, antiferromagnetism will be favored at very weak potential depths, whereas for something like a honeycomb Moire, ferromagnetism should be expected over a much broader range of Moire potential depths. And I should say that this kind of picture was recently corroborated by more detailed quantum Monte Carlo simulations from the Flatiron group. Yes, Oscar.
So if you go further to the right,
Yeah.
actually this should become some sort of a triangle lattice Hubbard model
Indeed.
with
Indeed.
a super exchange that's set by T squared over U.
Yes.
Does that recover? Do you recover that?
So I haven't, so let's see. You mean like numerically, are the exchange couplings comparable or?
Yeah, so
Yeah.
your green curve should become the super exchange. No?
It should, although I haven't honestly tried to map that in detail, but I think indeed when the Moire potential is deep enough, some kind of Hubbard-like description is more appropriate. And this does agree with what people have, estimated for the type of ground states.
If you look at mathematics
Yes.
order.
Yeah.
That means that it's 120-degree structure.
Good, yes, yeah, indeed. So in this case, when RS tends to infinity and it's only this two-particle exchange that dominates, the ground state will be a 120-degree antiferromagnet. That's correct.
Do you still keep U infinity if there's no?
So in these semi-classical calculations, yeah, U is in a sense infinite. That's right. Yeah, that's right. There's a hardcore and no double occupancy.
But this is hardcore at an infinite point, right?
Correct.
Or it's so once you have a lattice, you're gonna have a Wannier state, which is a finite width.
Right.
You can imagine the situation where two Wannier states are on top of each other. Is it gonna cost you finite energy or infinite?
Well, so in this, in these calculations, the electrons are always point-like. Yeah, so
But you see what I'm saying? If you have a deep potential, you're gonna
Yes,
form
of course.
a Vanier state
yes,
within that lowest band. Now,
Correct.
there should be a Hubbard model for those Vanier states.
100%. And that's how people traditionally study this kind of system. So this is approaching it from, a different limit where, yeah. Yeah, that's correct.
Yeah, that's.
Yeah, I mean,
Is that, because it's, I thought the super exchange was a different mechanism, right? That I have like one orbital on each site, and if
Yes.
I have, if I have one spin flavor, I can, I can never do a virtual exchange, but if I have both spin flavors, I could do the hop over and hop back, and I thought yours was explicitly these ones where you can't.
that's right. So this is a different mechanism of magnetism. Yes, correct. I think I was not clear. My answer, my point is just that when you start from a Hubbard model-like description, you actually get in the deep Maury limit the same answer. But it is in a sense, yeah, a different mechanism. Yeah.
Okay, but if I start to crank the Maury potential down, right,
Yes.
then I might wonder, so now I'm in this regime where actually the three spin term is dominant.
Yeah.
I might now wonder, well, what if I make you finite, right, and I, because presumably your model in that, if you had two spin flavors, would have these two squared over
Correct.
couplings.
Yes, but in the approach that I've taken here, I'm never really working on a lattice. So I don't, yeah, so I'm not sure how to
I guess
map
my
them.
question is
Exactly.
like, do you believe that those couplings are gonna be small compared to the ones that you're calculating here? Is there
Oh, I see. You're saying if I just literally looked at super exchange
just?
processes,
Yeah,
yeah, I think there'd be exactly zero, just because there would be, if I really have point-like electrons, there would be an infinite Coulomb energy to put them on top of each other.
okay.
Yeah, but it is, yeah, I haven't thought seriously though how to connect these pictures, although probably there is a nice way to do it. It's a different limit of the problem. Very good. So the upshot here is that different types of Maury potentials can modify the magnetism in qualitative ways. Okay, and another thing maybe to note is just that the degeneracy that we had in the homogeneous case in the absence of Maury is lifted quite rapidly by this Maury potential, so we can more unambiguously determine what the magnetism should be. Good. So let me put aside now these ring exchange processes and tell you about another type of quantum process that's interesting and perhaps even more important, which is the tunneling of defects in the lattice. Okay, so classically we understand that the creation of a point defect in an otherwise pristine crystal will cost you some positive energy. Okay, here I'm showing you the simplest versions, a vacancy and an interstitial. But now as this defect can start to hop around and tunnel through the lattice, that will of course lower the energy. Okay. Another thing that will happen is that the motion of the defect will exchange the electron positions, and this will also couple the spin degree of freedom. Let's ignore that for now. So in a cartoon, we can imagine the following situation. So here I'm plotting now the energy of a point defect as a function of the density of the system, the density of the crystal, let's say. So at very low density, when the system is very classical, we have some positive creation energy. And as we increase the density, quantum mechanics becomes more important, tunneling becomes more pronounced, and this energy spreads into a band, the bandwidth being of order of the hopping process. And so we run into a very interesting situation where the energy of a defect, or the bottom of this defect band, I should say, can drop below zero energy. If that were to happen, then one would expect this should trigger some sort of self-doping instability where the system spontaneously accumulates some finite concentration of ground state defects. Okay, the idea that such a thing could happen in a quantum crystal is not mine. It goes back to Andreev and Lifshitz, who are thinking about similar things in solid helium. This was the original idea behind the supersolid phase of matter. But now we're going to ask if something like this can happen in an electron solid. Okay, so
And these guys are called mechanicians.
right. Good. And let me just note that if this were to happen, if there was such a self-doping instability, this kind of defect crystal would be a distinct phase of matter from either the proximate ordinary crystal or the proximate liquid. It would really be some kind of metallic electron crystal phase, okay, or metallic density wave.
How does the self-doping stability, how does that work with charge conservation?
So I'm not changing, I'm not adding or removing charges. I'm saying, I take n electrons.
Oh,
and
it's just rearranged.
rearranging them to either have a defect or not.
I see.
Yeah.
And some population are mobile charges and some population.
Right.
I'll also give you a mean field picture of this later, which might be more intuitive actually. Good, so we asked if such a thing could happen, okay? So what we did was the same sort of semi-classical calculations that I described to you in the case of ring exchanges. So again, at large RS, when the system is semi-classical, these hoppings can be estimated by just semi-classical WKB methods. And so what we looked at were a variety of hopping processes. This is in the case of an interstitial. So in pictures, the hopping processes we considered are shown here. And these calculations were done by Kyung-Soo. And so here I'm reminding you this WKB formula for the hopping amplitudes. Okay, it's h bar omega times this exponential factor squared of RS times the dimensionless action. And the dimensionless actions with these different hopping processes are summarized here. Okay, and what I want you to note is that the actions are in some cases as much as 2 orders of magnitude smaller, okay, than they were in the case of ring exchanges. So the barriers to tunneling for hopping are much lower than they are for ring exchange. Okay, very good. So I should say that there's a similar picture one can draw in the case of vacancies, but that is a little bit more complicated. If there are questions, I can talk about that. So now let's ask ourselves, what does the energy of the defect do as a function of RS? Okay, and in particular, can we trigger such a self-doping instability? So here the energy of an interstitial defect, which is what I'll focus on for simplicity, is a sum of different terms. There's a classical creation energy, something positive. There's modification of the 0-point energy. Okay, but the most interesting term is this kinetic energy term, which is of order the hopping. Okay, and so the red curve here, this shows the energy of the point defect defined in this way as a function of RS. And what our semi-classical estimates suggest is that at a pretty large value of RS, roughly 70, indeed, the bottom of the defect band can drop below 0 energy. Okay, so this would then trigger this kind of self-doping instability that we were just discussing. Yes.
So you assume that the period of the crystal is fixed, right?
Correct, correct,
So you
correct.
cannot just rearrange and let this extra electron to be part of the piece.
Correct. Yes, indeed. Yeah, that's exactly right. So when we minimize the action, there's some, in principle, the true ground state of the system will be a pristine one, but the barrier for that is big enough that it doesn't happen. That's right. That's exactly right.
So, yeah, main question. So suppose RS is lattice at 7.
Yes.
So what's order? How's the impurities order?
So the impurities, there will be no impurities in the ground state of the system. There will be some pristine crystal. And what I'm saying, and okay, there could be magnetic order, that's what we were just discussing. But now what I'm saying is as you decrease RS, then the kinetic energy of the defects will become big enough that the system will spontaneously want to acquire some defects in the ground state. I'll give you a different picture of this in a second that I think will be more familiar.
And when some defects?
Yes,
And
and-
how these defects will be arranged?
Yeah, so, well, the periodicity of the crystal will change now. Okay, so there'll be a non-integer number of electrons per unit cell of this new state. And these defects, they'll form some kind of metal.
Why is it not melting?
What, it could, but if you look at, estimates of the melting transition, they're at smaller RS than this. Okay, so this is some kind of intermediate phase then. So let me show you a phase diagram, and I think maybe it'll help.
So you would say that Monte Carlo is definitely not melted at 7.
Correct. And yes, that's right. I mean, that's, maybe their wave functions just smart enough, I don't know. But yes,
Sorry, are you thinking about processes that create sort of pairs like one vacancy and one interstitial, because an electron just leaves the lattice?
so
And then we want to know when the creation of those, when we gain from creating such a pair.
no, I'm thinking about individual defects. Let me give a different picture of this that I think will help. Okay, yeah, good. So first of all, what I'm trying to tell you now is that as a function of the density, this is a phase diagram that I drew at the beginning of the talk. We have a high density liquid, a low density crystal, and now what I'm suggesting is the possibility of an intermediate metallic crystalline phase. Okay, our semi-classical estimates put the transition between these two at RS of roughly 70, but that can be refined. And one other thing to note is that because the energy of this metallic electron crystal will be lower than that of the ordinary crystal, transition between the metallic crystal and the ordinary liquid should also occur at a smaller value of RS. Let me give you a mean field picture of this evolution that I think will be helpful. So how do we understand at a mean field kind of Hartree-Fock level an electronic crystal? Well, it's nothing but a periodic potential, but one that is self-consistently generated. Okay, so kind of classically, we expect that self-consistent periodic potential to be one that has exactly 1 electron per unit cell. Okay, but nobody guarantees you that that has to happen, right? In general, the self-consistent potential, both its strength and periodicity are somehow self-consistently determined. And so all I'm telling you is that at intermediate RS, there's a possibility that that potential will be one with a periodicity that does not have exactly one electron per unit cell. That's it. So it's just, in a different language, this is just a metallic charge density wave state, which, again, in a kind of mean field picture would look something like this. Okay. It's just, we access this state coming in from strong coupling, but all I'm telling you is that, kind of in a Fermi liquid language, that there's a instability of the Fermi liquid to some kind of metallic charge density wave. That's it. Nothing more exotic than that. But again, we're accessing it from a different kind of side. Okay. So to summarize then, what I'm telling you is that there are significant quantum effects for the experimentally relevant range of RS. Something I didn't talk about, but that is quite interesting, is that the fact that these hoppings are so much larger than the exchange couplings means that the sort of defect-induced kinetic magnetism will also come with much larger energy scales than those associated with ring exchange. Maybe one other thing to note is that, this Fermi surface of this metallic charge density wave, it presumably has its own instabilities. And so, one thing that I'd like to try to understand is whether, for instance, there could be a superconducting instability of the system. So this might give you some kind of alternative to the usual Coulomb mechanism of superconductivity. Yes, please.
I understand this red ring as like, as you said, charges with coexisting with like metallic electrons form.
Yes. Yeah, that's right. Yeah, that's right. So you have some periodic potential. It's self-consistently generated. It doesn't fully gap the Fermi surface, and so you have this like remnant little Fermi pockets. Yeah. Yes, indeed.
No, just say, so the substance is charge density wave.
It is a metallic charge.
Metallic state with charge density wave order.
That's it. But we came at it from a very different side. That's it. Yeah. I
Is
think
there a way to test for this in separately small carbon?
I'm trying to help them. So they do this variational diffusion Monte Carlo, which is very good, but it is kind of limited by the type of variational wave function that you start with. And after talking to these guys quite a bit, this type of state would actually not have been within the class of wave functions they looked at. So I'm doing my best to help them engineer it. I think some preliminary calculations that they've done suggest it's competitive, but it needs to be energetically competitive, but it needs to be refined.
But is this the same as a super solid? That's the same object?
Well, so if these electrons,
Transparent Tisanovich and
so I think it would be indeed. So for instance, if these electrons condense into a superconductor, then it would be, very similar to the super solid. The difference is that, in the Andreev-Lifshitz case, you have bosons, they were considering solid helium-4. I have fermions, but yeah.
But when you say superconductor, electron liquid also in this respect can condense the superconductor.
But yes, it can. I'm just saying that, in this case, it's kind of natural because, these metallic electrons will interact strongly, presumably, with the phonons of the electron crystal itself. So you could imagine even some kind of generalized electron phonon mechanism. I haven't worked this out.
Energy normally gives this.
Correct. Yes. But in this case, what's different is that we've already taken into account the Coulomb interactions at the beginning. So we don't have to worry too much about retardation and things like that. Very good. So that's what I want to tell you about single layer two-dimensional electron gases. How much time do I have left?
Very good. You have 10 minutes.
10 minutes. Okay.
Let's 10 minutes, like 12 minutes.
Okay, let's see how we do. So in the remainder then, what I want to tell you about is a very simple way in which to enhance some of these quantum crystalline effects. And that's simply to consider a bilayer. That's it. Okay, so what we'll discuss now is a bilayer of two 2D electron gases, each of equal density for now, and separated by a distance d, and just coupled by Coulomb interactions. No tunneling for now, just Coulomb interactions. Okay, and what we'll see in a second is that this kind of crystal can realize new lattice geometries as a function of the interlayer distance. Okay, this crystal will also be stable to higher density than the single layer counterpart. The reason simply being that you get an additional commensuration energy gain by locking two crystals in the layers. This implies enhanced energy scales for the various kind of quantum processes we were talking about. And finally, the thing that I find most interesting is that these kinds of bilayer crystals apparently exist, as was demonstrated now a number of years ago in Han Park's lab. And if there's interest, I'd be happy to tell more about these experiments. So let me briefly now tell you something about these bilayer electronic Wigner crystals. So now, in addition to the density, that was the original axis we had in a single layer, we have a new axis, which is the interlayer separation. And so you get a sequence of structural phase transitions. Let me walk you through this. So when the interlayer separation is large, the layers are weakly coupled. As you bring the layers together, what will happen is that each layer will just form a triangular lattice and they'll just lock to each other in this way to minimize the Coulomb energy. Okay. And as you bring the layers closer and closer together, what you find just by doing simple electrostatics is that there's a transition from staggered triangular lattice like this to staggered square lattices. Okay. And again, because of this commensuration energy gain, the critical RS will similarly go down. And some old quantum Monte Carlo estimates put this critical RS as low as roughly 20. Okay. And as you bring the layers yet closer together, you'll get transition into this kind of rectangular lattice phase until the layers are right on top of each other, at which point you have again, a single layer, but now with twice the density. And that's why this critical RS is reduced actually, or excuse me, the critical RS is increased or the density is reduced. Okay, so you have this kind of evolution of phases. And so the question that we'll address now is what are the effects of multi-particle ring exchange, defect dynamics? Similar questions to what we were just discussing, but now in this bilayer context. Okay, so let's consider first multi-particle exchange. This is just, this formula is a reminder of what we had some slides ago, but now the difference is that the actions associated with different processes will be functions of the interlayer separation. Okay, we're going to neglect interlayer tunneling, so we'll consider processes in which electrons in a single layer exchange and the electrons in the other layer just adjust and try to get out of the way to minimize the action. So here's just a cartoon of some of the, or not a cartoon, these are the results of a calculation. This is in the case where each layer forms a square lattice. So you see these black, so the black and white corresponds to electrons in different layers, in the case that they both form square lattices. So you see, for example, when these two particles are exchanging in one layer, the particles in the other layer kind of doing a little dance to get out of their way. You can consider more complicated things. There's 3-particle exchanges, 4-particle, and so on. The point of this is just to show you that these are really highly correlated processes involving adjustments of the positions of electrons in both the layers. To quantify this, we look again at the actions associated with the different processes. Okay, there's a lot going on in this picture. So let me just kind of highlight for you what I want you to note. So this is the dimensionless action as a function of the interlayer distance in units of interparticle separation. The different colors correspond to the number of particles that are exchanging, and the different processes for a given number of exchanging particles can be inequivalent. So for example, when I have a rectangular lattice, I can have a 2-particle exchange along the short leg or the long leg, and that's why you have these two different curves here. So the thing that I really want you to note about this, again, without going into all the details, is that the least action path actually changes, or the exchange, the number, the action associated with, the least action path changes as a function of the interlayer distance. So when the interlayer distance is sufficiently large, the 3-particle exchange process still has the lowest action, but as you go through a first-order phase transition from this triangular lattice to what turns out to be this kind of rhombic phase, it's actually the 4-particle exchange that has the lowest action. And as you decrease the interlayer separation yet further, it's the 2-particle exchange that is most favored, and that continues all the way down until the interlayer separation goes to 0. So the implication of this is we can actually now make asymptotically exact statements about the nature of the magnetism as RS goes to infinity just by considering this evolution of the least action path. Okay, so we can turn this into a phase diagram. So let me just remind you that we have an effective magnetic Hamiltonian of this form, okay, sum over different permutations, where each exchange process comes with this kind of coupling coefficient. And so as RS goes to infinity, it's again the minimal action exchange path that dominates. And so as we vary the interlayer separation, we get this sequence of phases. Okay, when you have a stacked triangular lattices, you get a ferromagnet because the 3-particle exchange has the lowest action. In this phase, this kind of rhombic phase, because the 4-particle exchange has the lowest action, it turns out you get this kind of order where the spin winds by 90 degrees around a plaquette. And then eventually, when you're in the square lattice phase and the 2-particle action dominates, you get a pi-pi in the antiferromagnet. This is me.
You have only particular phases with either Niel or force ablative from magnetic force.
Yes.
Do you allow states within commensurate voltage for them?
So so good. So when RS goes to infinity, there's only one coupling that will dominate, And those Hamiltonians are sufficiently simple that we can read off what the magnetic ground state is.
Right.
Now, as you decrease RS, then you have a more complicated magnetic Hamiltonian with some competing couplings, and there the story is more complicated actually.
Right.
And you have to diagonalize a more complex magnetic Hamiltonian, and you get a variety of magnetic phases and corresponding transitions. Okay, I didn't bother putting that up because it's sufficiently complicated that I don't think it'll be very instructive, but it is interesting. And the other thing to note is that because this bilayer crystal is stable to higher electron densities, the magnetic energy scales, these J's, will all get a significant boost. And in fact, at intermediate interlayer separations, our estimates suggest that you can have exchange couplings that might be as much as 2 orders of magnitude greater than that you get in a single layer. Okay, good. So this is the last part of my story. So let's continue on with this bilayer. And now let's ask ourselves what happens if we just create a weak density imbalance. Okay, so let's start with equal density layers, and there's some lattice spacing that I'm calling A naught, and now we'll make a small density imbalance. Okay, of course, in any experimental system, the densities will not be perfectly balanced, so this is not an unreasonable thing to consider. In general, in fact, in these gated 2D materials, the densities in the 2 layers can be controlled independently. So this is, I think, quite a reasonable thing to consider. So let's imagine now we increase the density in the top layer a little bit. Okay, then there are different possibilities. Okay, either the lattice constant will, so the first possibility is that the lattice constant will remain essentially unchanged. And what we'll do is just inject some interstitials into the top layer. Okay, and of course the lattice will relax a little bit, but that's one possibility. Another possibility is that we increase the density and the lattice constant in the top layer gets squished. Okay, it decreases at the expense of creating vacancies in the bottom layer. And yet a third possibility is that we create some number of interstitial vacancy bound states in the 2 layers. Okay, so these are some of the different possibilities, but it turns out that which of these is most favored actually depends on the interlayer distance. Okay, and so what we found, this is together with Zecunzhuang, is that if you even just do simple electrostatics, there's a rather interesting evolution of the lowest energy type of point defect that you get. So it turns out that when interlayer separation is large, if you weakly imbalance this kind of crystal, then interstitials are formed. And so that's what I'm calling here an interstitial liquid. You'll have these itinerant interstitials that float around. If you further decrease the interlayer separation, it turns out that the vacancies are more favorable. And finally, when the interlayer separation is small enough, it turns out that interstitial vacancy bound states are what you want to form. And so these are sorts of metallic density wave or defect liquid phases that can be stabilized in a weakly imbalanced bilayer crystal. One thing that I'd like to look at is, again, the kind of tunneling associated with these defects to ask ourselves, what is the kinetic energy of their motion and what kind of states can be stabilized on these kinds of weakly imbalanced bilayers. So let me then conclude with telling you what we have learned, or what I hope you have learned. So I told you that these kind of electronic Wigner crystals appear to be ubiquitous across 2D materials. I've argued for you that in the experimentally relevant range of RS, these should really be understood as quantum crystals in the sense that we discussed. In the case of a single layer, monolayer crystal, point defects apparently have a very low barrier to tunneling, and this leads to the possibility of this kind of defect liquid